In today's class, we move on to Chapter 6 and consider the electronic structure of atoms. That's thinking about where the electrons are found within the atom and the corresponding energy. We're going to be looking at ideas in section 6.1 through 6.3. 6.1 considers the wave nature of light. When we think about light, we're talking about the electromagnetic spectrum. Light consists of two perpendicular waves, one corresponding to an electric field and one corresponding to a magnetic field. In this chapter, understanding the behavior of waves is going to be an important idea for us. The expression right here, c equals lambda nu, is going to be one that we want to know how to use. C is the speed of light, which is a constant. That'll be given for us, 3 times 10 to the 8 meters per second. Lambda corresponds to the wavelength, and nu corresponds to the frequency. Speed of light is a constant, and as we see, because these are a product, when one of these is larger, the other is smaller. If something has a long wavelength, it has a short frequency. If something has a very high frequency, it has a short wavelength. We'll also be doing some unit conversions between meters and nanometers. That's would be given to us, but it's going to be one that I think we'd want to memorize because we're using it quite often. 1 times 10 to the 9th nanometers equals 1 meter. Visible light is just one region of the electromagnetic spectrum. We see the entire spectrum here spanning from gamma rays all the way to radio frequency. Our learning objective here, we want to know the order of these regions, putting them in order in terms of frequency, wavelength, and energy. So if I'm looking over here on the left-hand side, gamma rays and X-rays, these have a very high frequency and a very short wavelength. The corresponding energy is high. Over here on the right-hand side, microwaves, radio waves, a very low frequency and a very long wavelength. And these are low in energy. So you don't need to know specific values, but you need to be able to put the different regions in order. Typical calculation is shown here. Calculate the frequency of red light. That would be light that has a wavelength of 725 nanometers. One thing that I find useful within this, when I'm using this expression, c equals lambda nu, is to also see what would be the wavelength, what would be the speed of light when it's in nanometers per second. I find memorizing that is helpful because a lot of times we're going to be doing conversions and the wavelength is going to be in the nanometer range. So the speed of light is 3 times 10 to the 8 meters per second because there's 1 times 10 to the 9th nanometers per meter. The speed of light then is 3 times 10 to the 17th nanometers per second. Now you could certainly do the conversion, but I find that's just helpful to know. We then have it equal to lambda nu, and we can solve for the corresponding frequency. To get a sense of the value, notice how the frequency here, really large number. That's something we'd look for. Take a second, make sure you're comfortable with the ideas on this slide. What questions do you have? Here's a pretty typical exam question. Which statements are going to be true? And so we have a combination describing aspects of X-rays, gamma rays, UV. So this is different regions of the electromagnetic spectrum. This is looking at the objective of knowing the order of the electromagnetic spectrum in these different properties. So if I were to look at this one, X-rays versus gamma rays, the gamma rays are higher in energy. X-rays versus blue light, X-rays have a higher frequency. They're to the left of my visible spectrum. Ultraviolet versus microwaves. Ultraviolet is to the left here, which means that it has a shorter wavelength, higher frequency. And then finally the infrared, we're considering a comparison there. So this whole setup right here, this would be how this could show up in a multiple choice question. Now, the characteristics of waves are going to be really important within this chapter. So let's explore a little bit the behavior of waves and look at some evidence that light has characteristics of a wave. So to do that, we're going to begin within the simulation by looking at waves that are in a tub of water. So our faucet's leaking, and we have waves that are spreading outward within the water. If we were to look at the side, we see how the water is going up and down, up and down. And that's what the top view is representing. The light and dark is representing peaks and troughs for the water. What if we switched it, and instead of having a tub of water, the source was a laser? Notice when we turn the laser on, we have, in this case, green light that's moving outward like a wave. If we were to look at a screen on the right-hand side, we would see how the light is striking the screen on the far right-hand side. We're considering light as a wave. Now, it's going to get a little bit more interesting when we go back to our tub of water and we have two leaky faucets. Both of these are now sources of waves. Notice how the waves interact with each other. If we were to measure that, we've got a device here to show how the wave is going up and down in that region of the tub. But along this diagonal, it's barely moving up or down at all. Along this diagonal, the waves are canceling out each other. The waves are interfering with each other, and the amplitude is being reduced. Let's see the same thing with the two different lasers. Notice the emerging pattern here. The waves are once again interacting with each other. They're interfering with each other. And we would have a region where the waves going up and down, and then along that diagonal there, it really cancels out the intensity, the amplitude of the wave, and it goes down to nearly zero. If we were to look at our screen right now, we would see that we'd have light and dark regions. Intense regions where the light is striking the screen, and then dark regions where the wave has canceled out. So evidence that light is a wave, we began by thinking, what would it take place with a physical wave like we'd have water in the tub? And we see that the same patterns are being reproduced when we think about light. This is going to be an important idea for us. Moving on to section 6.2. This involves quantized energy and photons. Two different experiments we want to consider here. The first is called the phenomena of black body radiation. So what's going on here? Let's say you have an electric stove. You turn on the electric stove, and what happens? Initially, the coils feel warm. Then they start to feel hot. Then they start to glow this orange color. As the temperature is increasing, the radiation, the electromagnetic radiation that's being emitted from that begins to change. Here's a simulation showing this. So on the right-hand side, we have a thermometer. As the temperature of our particular object increases, notice what happens. It begins to emit radiation to the right here of the red. That's in the infrared. Infrared is something that we perceive as heat. So as the temperature rises, the object begins to emit infrared, which we perceive as heat. As the object's temperature continues to rise, notice how the profile shifts. It now begins to reach into the red and then throughout the visible. That's what an incandescent light bulb is like. An incandescent light bulb is emitting infrared and then aspects of the visible region. If we were to take this even higher for an object, reaching all the way to the temperature of the sun, notice what the temperature of the sun emits. The temperature of the sun is going to emit infrared, so the sun gives us heat. It emits all of our colors in the visible region, and it's even reaching over to give us some ultraviolet. This is the profile that of a particular object. As its temperature changes, the energy that it emits as far as the region of the electromagnetic spectrum. This over here shows the data. Okay, this dark line, well, this matches what the simulation showed. The reason this becomes an issue is the very best physics in the world in 1900 predicted a very different profile. And when I say the very best physics, this is called classical physics. This is the physics from Isaac Newton on that was able to account for many wonderful things, but it failed in this respect because the profile that it predicted as a dashed line is just going up, 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 up. It's not coming back down. This dilemma was resolved by the physicist Max Planck. He provided a new theory, a new interpretation. His interpretation matched the experimental result, but it had a really radical idea. He said that the interaction between matter and energy was quantized. It takes place in specific steps. It's not continuous. It has a smallest value when matter and energy interact with each other. Now, this was really remarkable, novel, crazy, because it was thought that the interaction between matter and energy would be continuous, not have the small specific step size. The equation E equals h nu is going to be one that we used. This is the energy, nu is the frequency, and h, Planck's constant, 6.626 times 10 to the negative 34. That's going to tell us the step size for this interaction between matter and energy. And when I say step size, if we were to think about potential energy, this staircase here is quantized. It's showing that the potential energy could match as we're on one step or the next step or the next step. But what's really radical about this idea is you could never be in between steps if we could only be on the particular landing spots for the potential energy. So that staircase here, yes, it's showing quantized, but in a way it's even more remarkable than that. Because for something to truly be quantized, you could be on one step, the next step, but somehow never found in between. The other experiment that we have in section 6.2 is this phenomena of the photoelectric effect. The photoelectric effect is also going to demonstrate quantized energy. The experiment that we're looking at here was explained by Albert Einstein, and he wins the Nobel Prize for this. So within that simulation, we have a few different features. The way this is set up, we've got a piece of metal on this side. We're going to, and in this case, the metal is a piece of sodium. Light is going to be directed to that piece of metal. It's going to cause electrons to be ejected, and they go from this piece of metal over to this one. We measure the movement across by recording the current. So let's look at a few features of this experiment. So we'll begin by turning on the light, increasing its intensity. Right now, it's purple light. We see electrons now being ejected from the sodium metal and moving across. We could change the intensity of the light. That's changing the brightness of it. I still see electrons being ejected. Let's switch the metal. We're going to go to a piece of platinum metal. If we switch to a piece of platinum metal, we no longer have any electrons being ejected. Okay, so we have different variables we can change. I'd like you to make a prediction. What will cause electrons to now leave the platinum metal? Would we want to change the intensity of the light? Change its wavelength by making the wavelength longer, which means a lower frequency, or make the wavelength shorter, which means a higher frequency. Think back to what we said about the energy and the electromagnetic spectrum. Make a prediction, and then we'll check it out. Okay, so let's check. First of all, let's change the intensity. Changing the intensity higher or lower doesn't seem to make any difference. Let's change the wavelength. We're going to start by moving it towards the infrared. Longer and longer wavelength, lower and lower frequency is not doing anything. What if we make it a shorter wavelength, higher frequency? Nothing. Nothing. Okay, finally there's a difference here. So The key within this, the variable that was affecting whether the electrons would be emitted or not, it had to do with the frequency of the light. It did not have anything to do with the intensity. And as we move to a shorter and shorter wavelength, which was a higher and higher frequency, that's what led to the electrons being ejected. Now, this was a really radical experimental result that was interpreted by Einstein. Radical in the sense because light behaves in this experiment like a particle. It's as if the light, with its intensity, with its energy, E equals h nu, is behaving like a particle. And when that particular particle of light strikes an electron, if it had sufficient energy to eject it from the piece of metal, it would do so. And the reason I say this is radical, I just tried to convince you earlier that light in a different experiment behaved like a wave. But in this case, we have it behaving like a particle. If we were to take our simulation right here, we could turn on the light, and instead of having it shown just as a color, let's have it be shown as particles of light. Those particles are called photons. Each of the photons has a particular energy given by our expression E equals h nu. Within Einstein's interpretation, we're now thinking about E being the energy that a particular photon, a particle of light, has. Here's a typical question related to that. It says the energy from radiation can be used to cause the rupture of chemical bonds. So we can add energy in the form of light to break a chemical bond. A minimum energy of 242 kilojoules per mole is required to break the chlorine-chlorine bond in Cl2. Two parts to this question. How many joules of energy would be required to break just one chlorine-chlorine bond? And then photons with what wavelength would have that energy? I say break just one chlorine-chlorine bond because this is the energy for a mole's worth. How much would it take to break just one? So we see that 242 kilojoules corresponds to breaking 1 mole of chlorine-chlorine bonds. That 1 mole has 6.02 times 10 to the 23rd bonds in it. Then let's convert between joules and kilojoules. This would be the energy that it takes in joules to break just 1 chlorine-chlorine bond. That's a really small number, but that's expected. Okay. Photons with what wavelength would have this particular energy? Now we're going to use our expression E equals h nu. If we have our expression E equals h nu, that energy there is the energy for just one photon. So I'm going to take the energy of a photon, I divide by Planck's constant, I've brought the h over to the left-hand side. That then is allowing me to solve for the frequency of these photons. And then let's just convert between frequency and wavelength by using C equals lambda nu. This particular question, we're doing using both of these equations, E equals h nu and C equals lambda nu. That's something that we want to practice because this is a very typical exam question. Review the work on this slide right here. What questions do you have about the idea or about the calculation? Here's a similar question. So this is a sample exercise within the section. So I list here the relevant equations, different constants. We're going to stop the video here. Try to apply the ideas we saw in the previous slide to this one and work with a classmate as needed. Here would be my work. The question is, a laser gives off a pulse of infrared light that has a wavelength of 1054 nanometers. And we also know the total energy from that laser. How many photons would be in that particular pulse? So what I ask myself first would be, what would be the energy of a single photon given the wavelength of 1054 nanometers? So I converted to frequency equals C equals lambda nu. The speed of light I used back to that 3 times 10 to the 17th nanometers per second. That was equal to the wavelength times the frequency. So now I can solve for the frequency, really large number, which I'd expect. I took that frequency and I put it into E equals h nu. From there, I could figure out the energy that just one of those photons has. Really small number. One photon is 1.89 times 10 to the minus 19th joules. How many photons would it be if I had 2.5 joules? So I set up a simple proportion to figure out how many photons were involved. What questions do you have about this? Section 6.3, we're going to look at Bohr's model of the hydrogen atom. Up to this point, we've looked at different models for atoms, beginning with Dalton's model, modifying that as we learn more about electrons, and leading to Rutherford's nuclear model. Connecting the line spectra to the Bohr model, you're going to investigate that in the lab, emission of light and atomic models. And the next section that we talk about here, 6.3, really closely aligned to what you'll also be doing in the lab. Here are the different sections of the book on the Bohr model. Line spectra, Bohr's model, the energy states of hydrogen, and the limitations of the model. If we jump ahead to the limitations, we find this description how Bohr's model was an important step, but it's no longer the most comprehensive model that we use. We're going to retain a few ideas from Bohr's model. We're going to retain the idea that electrons are going to be only found in discrete energy levels, the idea that these energy levels are described by quantum numbers, and that energy is involved as an electron moves from one energy level to another. Those are all going to be kept in our more comprehensive model. So what do we mean by a line spectra? So a continuous spectrum of light is produced when white light is directed through a prism. If you have a light source that includes all of the colors, when you send it through a prism, the resulting screen will show all of the colors, Roy G. Biv. A line spectrum, however, does not have every color. How would you generate a line spectrum? If you put gas within what's called a discharge tube and send electricity through it, and this is something you're going to do in lab, you would find that when you then send it through a prism or use a grating, when it separates out into its component parts, it does not include every color. And different patterns were found depending on the gas that you put in the tube. Here's the pattern of light that you would see for hydrogen. Here's the pattern of emission lines for neon. Now, the hydrogen one was noteworthy because it could be explained mathematically with a very simple pattern. So mathematicians were aware of the line spectrum here for hydrogen, and they found that mathematically, just by using two different integers, they could explain the pattern. But they could not explain what was taking place within the atom that gave rise to the pattern. And that's something Bohr is going to work on. So within Bohr's model, it's bringing together three different sets of ideas. He's going to bring together the nuclear model that Rutherford proposed. He's going to bring together the line spectrum for hydrogen. And then the expression we've been looking at, E equals h nu, the thought that we have energy being quantized and particles of light as photons. There's three different parts to his model, three different postulates. We're going to look at each of these case by case. Let's begin by using this particular simulation. So within this particular simulation, we're going to have white light that's being directed through a container here that has hydrogen atoms in it. Notice what happens. The white light is passing through, and I say white light because I have many different colors of photons. Occasionally, a photon is leaving that box. When it leaves that box, it gets recorded here on the spectrometer. If you let this run for a long time, the resulting pattern is shown here. That bottom right, that's the line spectrum for hydrogen. So what's going on experimentally, it's as if we have photons of light interacting with the hydrogen, and it's leading to the emission of photons that has these particular energy values. That's what we're going to seek to explore. So within Bohr's model, here are the different postulates. Only orbits of certain radii corresponding to specific energies are going to be allowed. So notice within the simulation, At the very center is our nucleus with a proton, and we see an electron in an orbit, like a ring around it. It has a particular energy, and right now it's shown at the very bottom here. So our first postulate is, where could the electron be found? It's going to be found on one of these different rings. So it would be in motion around a particular ring. That ring we call an orbit. That's where the electron can be found. The particular energy value, when it's closest to the nucleus, it's at the lowest potential energy. That's called the ground state. The ground state is stable. It's the lowest in energy, and we're going to describe that by a number called the principal quantum number n. N is describing the energy. So the allowed energy values it could have would be the one corresponding to this, which correspond to different rings. Second thought, an electron in a permitted orbit is in an allowed energy. An electron in an allowed energy state does not radiate energy and does not spiral into the nucleus. This is the second postulate. What's this one about? So within Bohr, the electron could be in a particular orbit. In a solar system model, notice what happens. The electron is not stable. It goes spiraling into the nucleus. So this is a really big difference, okay? Within the Bohr model, the energy is quantized and has specific values. In the solar system model, it's not stable. So right there, this is the reason why Rutherford's initial model of describing a nucleus wasn't widely accepted, because that classical solar system model, there was no way using classical physics to explain why atoms existed. Energy is emitted or absorbed as the electron changes from one energy state to another. This energy is emitted or absorbed as a photon with our energy E equals h nu. This is going to be a really important idea for us. Let's watch the simulation to see what goes on here. So we have the electron moving around in its orbit. We send light through. Notice how the energy level for the electron changes. It interacts with a particular photon, and that photon moves it from a lower to a higher energy state. When it's in a higher energy state, farther from the nucleus, it doesn't stay there. It finds its way down in energy, moving closer to the nucleus. Each time it moves from a higher to a lower energy state, a photon is emitted. And that's what's showing up with the spectrometer. There's a lot going on within that simulation. Play this part again if you want to revisit it. Here I'll put into words those same ideas. So the electron is in an orbit around the nucleus. We can direct white light, a lot of different photons, into the chamber. It initially begins at n equals 1. That was our ground state, lowest in energy. If a photon strikes the electron, it will transfer energy to the electron if it matches the difference between the energy levels. If it transfers energy, and it will take the electron to move it from n equals 1 to one of the other energy levels, then that occurs. The energy will move the photon from being closer to the nucleus to farther away, from closer to the nucleus to farther away. It now has a higher potential energy. It doesn't stay there indefinitely. It's going to move back down towards the nucleus. As it moves back down, it could go in just one step, or it could go in a series of steps as it moves its way down. Every time it moves from one step to another, a photon of light would be emitted. And the spectrometer is recording those emitted photons. A lot of different ideas here about the process. What questions do you have? Let's look at a few features of this. So this is the different energy levels that we have here for the hydrogen atom. An important feature that's found for the hydrogen atom but not for other atoms, is that the energy levels converge. They get closer and closer together as our principal quantum number increases. Notice the largest gap is between 1 and 2. Then 2 and 3 is smaller, 3 and 4 is smaller, smaller, smaller. So the energy levels are converging. They're getting closer together as the n value increases. This is going to be an important pattern for us. In this particular figure, what's shown is that the transitions between n equals 1 and 2, 1 and 3, 1 and 4, all of these are taking place in the ultraviolet. The ones involving 2 and 3, 2 and 4, 2 and 5, these are all in the visible. 3 and 4, 3 and 5, 3 and 6, these are all in the infrared. Here's a few end of chapter questions on this topic. This is question 6.7. Consider the 3 electronic transitions here in the hydrogen atom, labeled A, B, and C. And we have 3 different representations for electromagnetic waves. Match them up. Which of the waves descriptions correspond to the transitions A, B, and C? Let's stop the video and give that a try. As I look at the different transitions, different waves, this wave has a really small wavelength, which would mean short wavelength, very high frequency, which means a high energy. If we go over here, this is our longest wavelength. A long wavelength would be a small frequency. And with our expression E equals h nu, a low energy. So this would be my high energy case, my low energy. Transition A has the highest energy. It's the largest energy difference between energy levels. And C here would be the smallest energy. That's how I'm matching them up. This one's similar to end of chapter question 6.46. Which of these electronic transitions for a hydrogen atom corresponds to the emission of the photon with the shortest wavelength? As I read this, a couple things jump out at me. They're talking about emission of a photon, and in terms of its energy, we're thinking about short wavelength. Emission, that means the electron's moving from a higher energy state to a lower one. It's moving from farther away from the nucleus, closer to the nucleus. That's what leads to the emission of a photon. In terms of the energy, short wavelength means high frequency, which means higher energy. So if I look within the choices here, I have 2 examples that are going to lead to an emission. They're initially at a higher energy level, and they're moving closer to the nucleus. These 2 correspond to emission. A and B would correspond to absorbing a photon. So out of choices C and D, they both lead to emission. Which one corresponds to the higher energy? The transition between 3 and 1 has a higher energy. I'm thinking about that because for the hydrogen atom, the energy levels converge. Even though the difference between 3 and 1 just is n equals 2, and n equals 2 between 4 and 2, between 3 and 1, it's a larger energy difference. So this would correspond to the emission of a photon with the shortest wavelength. We return back to the limitations of the Bohr model. What we're going to keep as we move forward is that electrons are found only in discrete energy levels that are described by quantum numbers. We're going to keep that idea. And we will also keep the idea that energy is involved in the transition as the electron moves from one energy level to another. However, Bohr's model left us with quite a few unanswered questions. He said that the ground state, n equals 1, is stable because the ground state is stable. That's not a very satisfying answer. If we try writing that on an exam, it works because it works. We're probably not going to get very many points for that. Another question, why could the electron be found at n equals 1, n equals 2, n equals 3, but never in between? How does it move from one to another if it's never found in between? That seems crazy. And why does the electron only move if the energy difference is appropriate? If it's only going to move from n equals 1 to n equals 2 if the energy was the appropriate amount, how would it know it's the appropriate amount if it never made the trip? Those are some ideas that we're going to take up when we move to our more comprehensive model, Schrodinger's model of the atom.